I suck at chess. So what am I going to do? Cheat. The first step in building a chess engine is deciding how to represent a chessboard. A straightforward idea is to use a 2D array, where each square holds a value representing the piece on it. While simple, this approach isn't the most efficient. A much better option is to use bitboards. A chessboard has 64 squares. A bitboard is a 64-bit integer. Each bit represents a square on the chessboard. This allows us to represent the position of all white pawns, for example. To check if a specific square is occupied by a white pawn, we create a bitboard with only that square set to 1. By using a bitwise AND operation, we can check if the square is occupied. If the square isn't 0, it is. This method allows for extremely fast move generations, since modern CPUs are optimized for bitwise operations. To represent the entire chessboard, we use 12 bitboards, one for each type of piece. A fast way to handle millions of chess moves per second. Not every piece is allowed to move everywhere. Pawns move forward and capture sideways. Rooks move on the vertical and horizontal. Bishops slide across the diagonals of the board. Queens move like rooks and bishops combined. Knights move in an L-shaped form. And kings can move one square in any direction. There are some special rules like castling, en passant, and promotions, where when a pawn reaches the last rank, it can convert into another piece. The only concept not yet implemented is check. Right now, if the king is under attack, you can't just ignore it, like so. You can still make moves that leave the king in check. To detect if the king is in check, I iterate over all enemy pieces, generate their possible moves and attacks, and store them in a separate bitboard called the threat map. Forming a bitwise AND between the king's position and the threat map, I can easily see if the king is under attack. Now we can filter all the legal moves. The way I did it right now is a little bit ugly. I take each pseudo-legal move and play it out on a copy of the current game and check if that move leaves their own king in check. If so, we know that the last move is illegal. Let's start with the simplest chess engine possible. It looks at every legal move and picks one randomly. I win, of course, but that wasn't exactly fair. The chess engine plays as if it wants to lose on purpose. So how do we make it smart? If you watch grandmasters play, it's like they just know where to put their pieces. Chess players don't think of each position from scratch. They recognize patterns. How do we teach a chess engine to do the same thing? We give it a brain. And by brain, I mean a bunch of numbers in a table. For every piece, we create a table that tells us where it should be. Take a knight, for example. It loves the center of the board, because from there, it can jump to many other squares. So squares in the middle get a higher value. Now, instead of just picking a random move, the engine will aim to put its pieces on good squares. So now our engine knows where to stand, but now it needs to know when to fight. In chess, capturing pieces is usually a good thing, unless it's a trap. So when do we capture and when not? Every chess piece has a value. A pawn will be won, and all the other pieces will be scored relative to the pawn. By adding up the white pieces and subtracting the black ones, we get a score. The more positive, the better the position is for white, and the more negative, the better for black. So the engine looks at all the legal moves, makes one move at a time, evaluates the position and chooses the one with the best score. If it spots a shiny capture, it grabs it with zero hesitation. However, if we calculate further, the black king will capture the rook, resulting in a draw. So taking the pawn is bad. To win, the engine needs a plan, and that plan is called search. This is where the famous Minimax algorithm comes into play. The Minimax function takes two inputs, a chessboard position and the depth, which determines how far ahead the engine will look. For this example, we assume there are only 3 possible moves, and we'll search the depth of 2. As a reminder, white tries to maximize and black minimize the score. We start by calling Minimax on the initial position and setting a variable to a very low value as a placeholder for the best move white can achieve. Next, we generate all possible moves for white, simulating them and calling Minimax on the resulting positions, with a depth reduced by 1. At this point it's black's turn, and since black is trying to minimize white's advantage, we approach it differently. While we initially set white's best score to a low value for black, we do the opposite. We start with a very high value. From here, the process repeats. We generate all possible moves for black, simulating them and calling Minimax on the resulting positions. If we reach the desired depth or the game is over, we return an evaluation of the position. If the return evaluation from a child node is better than our current best score, we update it. This process repeats for every possible move until we return to the original starting position. If we run the Minimax algorithm with a depth of 4, we would evaluate roughly 400,000 positions, which takes 5 seconds. However, if we run it at a depth of 5, nearly 10 million positions, which takes far too long. To solve this, we can cut down the search tree. After white evaluated the first branch and went down this path to find the -4, this parent node will be -4 or lower, because black is minimizing the score. But because white already has found a better position, -2, it will never choose this branch, so there is no need to calculate this branch any further. Now it only takes us 500,000 positions or 13 seconds, which is 10 times faster than before. The goal is to increase the positions per second. Even minor adjustments help a lot. For example, instead of calculating every knight move from scratch from every position, we can just pre-calculate every knight move from every position and put it in an array of bitboards. Now we have a lookup table, which is much quicker.